Moving on to our second talk, bit stealing made legal, is presented by Baudon. Tess is a third-year PhD student in Lyon, France, supervised by Gabriel, Radanne, and Laure Gonnord, working on programming languages and compilation. She's currently working on custom, finely optimized low-level memory layouts for algebraic data types, aiming to let programmers writing high-performance applications use ADTs and associated construct like pattern matching. Her work introduces a type system and a principal compilation technique for expressing storage format choices and optimizations for algebraic data types in a high-level language. This not only improves efficiency of the compiled function programs, but also provides a degree of control and expressivity that is often only found and implemented ad hoc in low-level systems-oriented language. We believe this work and any future works like it are invaluable in expanding capabilities of functional programming by improving the performance capabilities and expressivity. With that, Tejas, would you like to take it away?
Hi, can you hear me properly?
Could you speak a bit louder, maybe?
Yeah, I'm going to try to increase my microphone gain.
I think this works.
How's that?
Tess, could you speak a little more?
Yeah. Can you hear me properly now?
Great, awesome. We hear you.
It's loud enough?
Mm-hmm.
Awesome. So is everything ready? Can you go? Okay, so go. Okay, so what I'm going to present you is a paper from ICFP 2023, which is a joint work between me and my PhD supervisors. It's called Bit Stealing Made Legal because it deals with making low-level memory optimizations like bit stealing legal as in nicely abstracted way and correct. So the link here on this slide is linked to an online demo, so you can go play with this if you're interested. And yeah, this work is implemented in our compiler, which is called Ribbit, and so it's an online version which is accessible here. So what we're targeting, what we're interested in, is basically programs that need performance or low space usage or some other similar constraints, and that also have to use some sort of inductive data structures. So inductive data structures are used basically everywhere. They include various kinds of trees, such as red-black trees, such as the one that I'm showing here. And in order to deal with this kind of structures, there are two really neat language features to have, which are algebraic data types, or ADTs for short, and pattern matching. So ADTs are types that combine sum and product types. For instance, here we're going to model red-black trees with two sum types, color for just red or black, and RBT for the actual trees. So each of these two sum types have two possible tags, two possible constructors. So for example, for color, we say that the color of a node is either red or black. It's necessarily one of those. It can be anything else, and it has to be exactly one of those tags. And with this, we can constrain the shape of data, which is really comes in handy when we're dealing with inductive data structures. And when it comes to the actual RBT type, we can say that inside, so a tree is either empty or not empty. And if it's not empty, it's a node with a color and an integer value for the root. Here we decide that we're going to store 64-bit wide integers. And then we have left and right subtrees for dealing with binary red-black trees. And each of them is also a red-black tree. And so here what we're doing is that we're aggregating fields of different types together. This is what we call a product type. So algebraic data types in a nutshell, are any type system that enables you to combine products and sum types. So here we can see that with ADTs, where we can quite easily and intuitively model regular trees with a mounted inside active value. And so here we're going to go with integers for simplicity. And ADTs are especially useful when we combine them with pattern matching. What's pattern matching? It's basically writing functions by inspecting the shape of the data. So for instance, here we're going to write a function called cardinal, which counts the number of nodes in a given red-black tree. So obviously, if the tree is empty, it has 0 nodes. And if the tree is not empty, we're going to count 1 for the roots. And then we're going to recursively call cardinal on the left and right subtrees. So it's quite concise and it's also safe. We get static guarantees that come with ADTs. Here it's quite immediate just looking at it that both cases, empty and node, are dealt with. We can derive the type of each boundable, like T1 and T2. We immediately know that these are red-black trees. We're not trying to deal with nonsensical data. We just have empty and node, which are possible cases according to the type. Pattern matching is especially interesting for operations that inspect nested structures, like this rather complex rebalancing operation on red-black trees. So this is just an excerpt, but it's relatively concise and readable, at least when we compare it to patternless alternative that we're going to see right after. Why it's concise and relatively readable is because we follow the structure of the data to express control flow. What you need to do here is to determine whether the first color of the node is black, then bind some symbol to its integer value, and then look inside nested constructor to determine the colors of children of the root node. It's quite complex to express this without pattern matching, but thanks to pattern matching, we can deal with this kind of structure with more safety guarantees and with more comfort for the programmer who has to write this. And so when dealing with these kinds of structures, we most definitely want to use a language that has these features, that has ADTs and pattern matching. So we have established that these features are useful, that we want to have in our language. And the next question is, what about the performance cost of these abstractions? Usually in the height of a language, every abstraction, every nice tool comes with a performance cost. And when it comes to pattern matching ADTs, the answer is that it mostly comes down to the choice of memory layout that we're going to use to represent data. The problem is that compilers for languages with ADTs and pattern matching, so think OCaml, Haskell, functional garbage collected languages, typically they assume a fixed and somewhat uniform naive memory layout. So here's an example of such a naive representation using a sort of graphical language I keep using for the rest of this talk. So the empty tree is represented by the null pointer, or 64 bits. We're just going to assume that we're dealing with a 64-bit architecture here. And a non-empty tree, a node, is always behind a layer of interaction, behind a pointer to a struct or block, in which we take up a whole 64-bit wide word for some header containing some metadata. Then 64 bits just for a color, which more will only need 1 bit to store its a binary information. And finally, we get the rest of our data, so the integer that we actually store, a pointer for the, and here we have the 2 subtrees, so a pointer for the left one, which is not empty, and null for the right one, which is empty. And it is really a problem in the real world, because in the real world, inductive data structures are also used in performance critical applications, like the Linux kernel. And with Linux kernel, they use red-black trees, but since it's written in C, they don't have access to pattern matching or ADTs. And anyway, an operating system kernel has some performance needs that simply aren't met with the uniform representation we just saw. So in Linux, red-black trees follow a memory layout that is optimized for performance and especially for space. So if you look at the layout there, you can see that compared to the previous naive layout, we store more information in less space. This layout makes use of an optimization known as bit stealing, which is what is going on right here. If you can see my mouse, I think you can see my mouse. So the pointers, I can have a larger pointer. Anyway, so the layout makes use of an optimization known as bit stealing. Since regulatory pointers are broad aligned, the lowest significant bit is always going to be 0. And here we're going to use the three lowest significant bits to store the color information. And it prevents us from allocating a whole extra word just for a Boolean. But the downside of this custom finely tuned layout is that it requires control of the quite low-level details, which is only available to languages like C. So in the kernel, data types are written using C structs, and the whole data manipulation code is polluted by the clever tricks that we used in the layout. So if you look at just a simple accessor, so here's the parent pointer, which is here. You can see that we have to mask off the lowest bit because maybe it's set to 1 and that wouldn't be a valid pointer. Then we have to dereference it, and then we have some pointer cast thrown in for good measure. And if we look at the rebalancing operations, especially clumsy and quite painful to write and maintain. For each match case and the pattern matching with order, so this is just one line from the previous example, we need 5 to 10 lines of code in C. So obviously, it's not an ideal situation. And to top it off, we completely lose the static guarantees that come with ADTs. So whether this low-level memory layout properly models what the user actually had in mind with these regulatories, whether this kind of code is correct, it's all left up to the programmer, to the user, and obviously this leads to errors that are to bugs that are hard to find, hard to fix. Which is why our main goal in this work is to combine hand-tuned, arbitrary low-level memory layouts that user can specify with nice abstractions, namely ADTs and pattern matching. So we achieve this by providing a specification language for specifying custom memory layouts, or ADTs. So it's the whole green exploding node going over there. We add that onto the traditional compilation pipeline in black. So the main idea is that user specifies an intricate representation once with a memory type, and high-level data types and manipulation code, that is matching, they remain the same as what they would be with naive representation in high-level language. We also provide formal criteria to ensure that a given memory layout agrees actually with a given ADT, and just to be able to compile this kind of program, we provide a new pattern matching compilation algorithm, which is capable of emitting low-level code that deals with data represented in whatever way we specified. And this is all implemented in our compiler called Ribbit. And again, this is a link to a demo if you want to go play with it. So we're first going to focus on the memory layout specification part, or the DSL or language part of the contribution. And also going to quickly go over the agreements for more criteria. So we're going to use this example, Linux-like regulatories, to present our memory layout DSL. So we adjusted the types a little bit because we only deal with immutable data. So this is what Linux-style regulatories will look like for immutable data. We use a single bit for the color, it's 0 for red, 1 for black. And when it comes to trees, empty is a 64-bit wide word with its lowest bits at 1 and then unspecified padding. We don't care about what's going on in 63 highest bits. And note is going to be a 64-bit wide pointer with lowest bit set to 0 to distinguish it from empty. The second lowest bits used to store a color with the bits linked to this order. And then it's going to point to a struct with 3 fields. So the integer value and then the representation of the 2 subtrays left and right at the end of the pointer. So we're going to see how we can express the layout in our DSL in Ribbit. First, going to see how to specify a very simple sum type, which is color. So in our language, every custom type consists of an ADT, high-level type, then the keyword represented as, and then the actual layout specification, which we call a memory type. So the only information we have to encode for color is its type, which is either red or black. And whenever we want to specify different representations for different constructors, we're going to use a memory type construct, which is called a split. So here we use the keyword split to introduce that. And they're kind of similar to dependent types in that they express that the process type, the process shape of the value we're dealing with depends on some discriminant value. So here we're going to have two split branches, one per tag. So each branch consists of a discriminant value, here it's 0 or 1, that is which concrete value in memory identifies this branch. Then it gets a provenance, which is the actual link between source or high level and memory types. It indicates which tag or tags this branch applies to, which constructors this branch tries to capture. And finally, on the right-hand side of the split branch, we get the specific memory type that represents values of this shape. In this case, we have 0 on the single bit for red and 1 on the single bit for black. And so this memory type encodes the desired representation, which is a single bit set to 1 for black and 0 for red. So with such a simple type, we haven't gained much compared to C, and so we're going to see what happens with a more complex type, which is the actual RBT type. So it features a stack with several fields inside, with a prototype nested inside a node constructor. And we also want to express a rather fine aspect, which is bit stealing. Since we're dealing with an enum of some type, we're going to start with a split. And this time, we're not going to inspect the whole memory value to determine whether a tree is empty. We're just going to look at the lowest bit. So for this, we specify a discriminant location next to the split. And in this case, we use this path 01. It designates the lowest bit. It means start at offset 0 and take exactly 1 bit. And this is a part of the memory value we're going to use to distinguish between tags. Again, we get two split branches, one for empty, one for node. Just two branches is why it's enough to have 1 bit to distinguish them. We specify that the lowest bit is 1 for the empty tag and 0 for nodes with discriminant values and provenances, just like before. And in the empty case, we only need to specify the lowest bit. And we do so using this construct here, which is a bitword content specification. So here on the left-hand side, the underscore here means unspecified contents, but I want a 64-bit wide word. And then I'm going with the width and bitword content specifications, going to specify distinct parts of this word. And so here what I'm saying is that the lowest bit must be filled with the constant 1 on 1 bit. Sorry. And so this is how it represents how I want to present the empty constructor. So notice that it is redundant with a split left-hand side, which already says that the lowest bit is set to 1. We could leave it out and let Revit infer the specification, but here we're going to look at the full expanded memory type. Now, if we look at the more complex node tag, it's a little more complex since we also need to fit 4 fields inside. So we first specify a 64-bit wide pointer with the ampersand here, whose 2 lowest bits are going to be free due to address alignments. So we're going to specify the content of each free address and each address alignment bit. And lowest bit is going to be set to 0 with the same width bitword content specification constructs because it's used as the split discriminant. It's a tag. And the second lowest bit here, started offset 1 gets 1 bit, is going to contain the color, which fits into a single bit because, again, it just has 2 constructors. And we specified the memory type for color earlier. And what we're going to do is, in order to describe this bit stealing construct, we're going to encode the color using a construct that we call a fragment. Fragments express that some parts of the source value, the high-level value, should be represented right here, following some memory type. So here we say that the field C within the node constructor has to be represented here, encoded using the color memory type we defined earlier. And together with split provenances, these fragments are really what ensure memory types to the source algebraic data type. So now if we look at the structs pointed to by our 64-bit wide pointer, it has to contain 3 64-bit wide fields, which each encode a field from the node tag of the original type, again using fragments. So the field V is encoded in the first field on 64 bits with this primitive I64 type. and then left and right subtrees are recursively represented in the second and third fields. And now we can see that we have covered all data from this tag, from node tag. And finally, we get a memory type which specifies a complete layout for the arbitrary type. Now, what's not really immediate from just the specification is why this memory type is suitable for encoded regulatory values. So for this, we have several formal criteria that define the agreements between a high level and a memory type. So the full description is in the paper, but here are the two main ones. In orange, we see distinguishability. Intuitively, it means that we deal with some types by ensuring that all tags, all constructors can be told apart by inspecting some locations. It may be one or more split discriminants, but we need some way to distinguish between empty and node. And the second important criterion is coverage, is so here in blue. And it says that to deal with product type, we ensure that all data from the source ADT appears in some form, it doesn't matter which, but it appears somewhere within memory type. And so here we can see that each of the 4 fields maps to a fragment. And so these 2 criteria are met. So far, we have focused on types, on the input language, and now we're going to look at data manipulation code and how we compile it. More precisely, how we can use the memory type during the pattern matching compilation process to generate low-level code that deals with data that follows our custom memory layout. So the syntax is unchanged. Well, the pattern matching syntax is unchanged from some generic typical functional language. In this talk, it mostly be a mix of Open and Rust syntax. But anyway, since the syntax is unchanged, it means that we must compile high-level code to lay out specific machine code. And in practice, it means that we compile pattern matching to decision trees, which consist of switches, which we're going to show as rectangle in examples like this one. And after the switches, we get some leaves in green here. And what's going to happen is that each switch is going to inspect some memory location within memory value and to gain more information about which value we look in at, what the shape of the value is like after each switch. And when we issue leaf, it means that we've fully determined what the shape of the value was and that we're able to determine which, if any, case matches the value. So as an example for our compilation process, we're going to use this synthetic example on regular trees. We're going to isolate empty trees, non-empty trees that specifically have a black color for the roots and an empty left subtree. And I'm going to redirect all other trees with the white cut here to another case. So this is a decision tree we're trying to create. The first step of computation algorithm is to build sort of scaffold, a skeleton decision tree whose structure reflects that of the memory type. So far, every leaf is empty. So these are the leaves, and everyone has the empty set because we haven't added any information about the patterns yet. We'll populate by them with pattern IDs later on in the next step. So basically, that empty set that means that no pattern currently accepts values that reach again length. However, we've captured the structure of the memory type. Here you can see that the split was translated to a switch on the same location, and that whenever we have some type that aggregates different data together, like a struct or some word-like type with several bit-word content specifications, we get a power node. Power nodes, they used to group together parts of memory type that do not depend on each other. It doesn't matter if we look at, say, the left subtree before or after the right subtree. So these nodes express that. So we're actually not emitting parallel code for that, but it doesn't matter the order in which we perform the operations of this. Basic semantics of that, it's intuitively, if we're going to basic semantics of this node is that we're going to simultaneously evaluate each subtree and the integer, and the integer, any input value is going to be accepted if and only if all branches of the power node accept it. So this is going to be clear with the next step, which is called weaving. We just captured the structure of the memory type of scaffolding, and we're going to add pattern information. So this step, weaving, weave each pattern into the tree. Its goal is to populate leaves with pattern IDs and to expand parts of a tree when we need it to inspect nested subgroups. So we proceed by following the shape determined by the memory type with choices at switch nodes depending on the pattern we're currently weaving. Here we're going to start by weaving the empty pattern into the tree. The pattern ID here is going to be A, the output. So the empty tag is always set the lowest bit to 1, and so we only explore the 1 branch of the switch. Then we reach a leaf, which means that there's nothing more to match or to inspect, and so we add the pattern ID A to this leaf, which means that the pattern A accepts any memory value that reaches this leaf. Now we're going to weave the second pattern, which only accepts nodes values. So we're going to consider the 0th branch of the word switch and any of this one. Then we insert 2 parallel nodes, which correspond to the pointer and struct in the memory type. So we're going to recursively explore every branch of these power nodes. One of these branches is a leaf, just like the previous pattern, so we add the output ID B. And then we're running into an issue because the leaf here, highlighting green, corresponds to the color field, but we're not done matching the color field yet. We can just add the output ID here because the pattern does not accept any kind of color value. It only accepts the color black as opposed to red. And what we need to do is to express the fact that we only match the constructor black. And since the leaf is annotated with a memory type color here, it's what we call a bud as opposed to a leaf. We're going to grow a new memory tree in place here so as to inspect values of type color. So this is what happens here. We replaced the bud with a switch with 2 branches. We scaffolded a new tree from the memory type color, and so we get a switch on which we weave the subpattern black. And this is how we get up the output identifier B on the leaf coming from the 1 switch branch. Moving on to the second field, the integer values. In the subpattern is a wildcard. It doesn't matter. There's no need to grow the buds into a tree. We treat it like a leaf. We add B to indicate that we accept any integer there. For the left subfield, again, the pattern does not accept any red block tree values. We grow the highlighted RBT bud here. We get a new RBT scaffolded tree. Since we only inserted empty trees here, add the identifier B to the leaf from the 1 switch branch. Moving on to the last field, the right subtree have a wildcard, so we just add the pattern ID to the leaf. Last pattern we have to wait as a wildcard, so we accept any kind of value, and we're going to add the pattern ID C to every leaf and bud in the tree, exploring every branch. And the final step in the compilation algorithm is a short time, so keep it quick. Every pattern has been woven into a tree. All relevant information is encoded, and we can focus on simplifying, optimizing the decision tree to make it executable. So we first discard tapping information, that is, we turn buds into leaves, and also perform some generic transformations. Here we're going to merge equivalent branches together, and we're left with the following decision tree, which in which contains 1 parallel node. And so basically what we do here is that we use classic algorithms from that, because the problem of choosing an order in which we evaluate these 2 branches is already known in state-of-the-art matching compilation algorithms. So we reuse some classic algorithms from this community for solving this problem to choose a branch on which we grab the out branch, and after sequence serialization, we get the following decision tree. And so it's kind of broken a little bit. Anyway, at some point, Ribbit was able to compile it to LLV and IR, and you can see that it has the same structure. And so here's how we actually compiled pattern matching to an executable code that took a custom layer of data. Yeah. That's going to end. So yeah, this was the Ribbit approach with the input language for custom memory layouts, pattern matching, and the compilation algorithm that went with it. Thanks for listening to me.
Great. Thanks for the talk. I just want to quickly check, do you hear this mic?
Did I share this mic? No.
Do you guys or no?
Sorry, can you repeat?
Do you hear Okay, that's fine. Like, I guess we have time for like maybe one quick question, if anyone wants to. Oh. Right. So we have one question from in-person attendees room. Please go ahead.
Hi, thanks. The work is lovely. I have a question that's maybe this is not the best. It's not the best fit, but I'm curious about your thoughts. Anytime there's two languages interacting, you end up with a similar sort of problem, right? One way to look at what you're doing is there's sort of like a OCaml or Rust representation, and there's like a C-level representation. So another place where this kind of problem shows up is when you're doing, say, gradual typing, and so you have some code that's still working in like the untyped language and code that's working in the typed language, and you still have to do this sort of mapping. Have you thought about this? Are there reasons your technique wouldn't apply in those kinds of settings? Because it's a practical problem that shows up there as well. Thank you.
When it comes to practical application of say, Revit in these kind of situations, I think that it could be useful as some sort of intermediate representation to bridge the gap between the low-level sort of untyped language and the higher level language, which has a more strict typing discipline. And when it comes to the actual problem of trying to make some, if I understand it correctly, the problem is to make some low-level program to understand what it means to deal with a value that has some type in the higher level language. And so I can say exactly how we could integrate Revit with, let's say, the low-level language to teach it, so to say, how to interact with a value of a certain shape. But I think that the language part, the memory type specification part, could be useful to formally specify what it means in terms of memory representation to be a value of some type. I know if it answers your question.
Let's thank our speaker again. And Thais, if you could stop sharing, that would be great.
Sure, sorry.
Great. So,
thanks.